Hi, I'm Phil, and we're going to continue with one of my Airbit2 projects. And just to revise what the Airbit2 is, we'll just look at the description. And we've previously had a video on the Airbit2 and how I'm learning to fly it. So the Airbit2 is a microbit-based drone, and it uses a lightweight construction for its frame, has a lithium battery, and 4 DC motors. And it has 2 sensors in the IMU. There's an accelerometer with 3 degrees of freedom and a gyro with 3 degrees of freedom. And there's the possibility of adding additional sensors via the I2C port, such as a barometer. And you control it with programming, and you use a remote control, which is a second microbit computer. Okay, so let's have a look at my more recent project. So we'll go over to projects, and you can see that I've done a few. The last one is looking at balancing boards. And I had quite a few attempts at this, but the most recent one was more successful. So if we actually look at the hardware for it, I'm using the 2 microbits, one for a remote control, and the other one's on a balancing board made of Lego pieces. So a bit like a seesaw. So you can see that the microbit is in the middle, and on either end of the seesaw are 2 of its motors. And the whole purpose of this is to try and balance the microbit and explore the concept of PID. Okay, so here we can see the motors, the balancing board, and it's in full swing on the lower picture. So yes, the objective is to demo PID algorithm to balance the 2 Airbit 2 motors, and to change some of the coefficients of the PID algorithm to see how that affects. And we're using that second microbit to make it a bit more safe. Okay, here is some of the background. I've been talking to Henry Peterson, and he provided the software, and also provided 3 files. So a balancing board made out of acrylic or a ply board could be built. So we've had a little bit of discussion, and I thought it would be a good idea to have one of these. So, but I'm using Lego parts, and the software, I'm going to use radio to communicate. So between the 2 microbits, and this is a safety measure. So A will be for to arm. So if I send an A via the radio, and all I have to do is just press the buttons on the microbit A and B on the remote, and it will transmit an A. Alternatively, it will transmit the demo number. And I've only got one demonstration at the moment. It's a single demo for the PID, but it's intended to have other demos to change the coefficients later. Okay, so let's have a look at the hardware. We've got the microbit, the Airbit, and the Electrex joystick. So we're beginning to run out of buttons on the microbit. So we're using the joystick with more buttons. Software-wise, we've got 2 microbits, so we've got different software for each of them. One's the sender, and we're using Makcode for that. And there's the sender code, and we've got the balancing one. We'll concentrate more on the balancing one. And the whole idea of the balancing board is to use the PID algorithm. And what we might do is stop that and have a look at the PID. So we'll explore a little bit about PID before we look at the software. And here I'm going to look at walk through the presentation. And what's PID? Well, it stands for proportional, integral, and differential. And so you can actually see the 3 portions, and it can be expressed either in this block diagram or mathematically. And it's an algorithm that helps us to steady and maintain a constant position for our drone. So you can see that the components there, and an important one is the set point. And our set point is the horizontal position. So let's have a look a little bit more. Okay, so they're the terms. And the origin, these are the people who contributed. And while it isn't used on the steam engine control, so we had James Watt originally designing a governor. And the whole idea here was to actually control the throttle and provide a constant speed for our steam engine. And we had Sperry, who contributed quite a lot to the gyroscope, but the person who actually contributed more than anyone else to the theory behind it was Nick Minorski. And his concept was used to control the steering on US Navy ships. But it's gone a lot further since, and you can use the PID algorithm to regulate parameters in industry like temperature of manufacturing, pressure, force, feed rate, flow rate, if it's involved in fluids, the chemical composition, the weight, the position, and the speed. So it's made an important contribution in industry, but also in things like stability. And here we can see a couple of gyroscopes on a US transport ship, the Henderson, being constructed in 1917 to give it gyroscopic stability. And this has contributed to aircraft carriers to enable them to land and allow the takeoff of airplanes on aircraft carriers using a stable platform. And it's used in navigation in lots of places, cruise control, even rockets and drones. So it's had quite a lot of use. And what it requires is a set point. So you've got to know what your goal, what your position is that you want to control. And this is our target. Tuning-wise, we have to optimize the control algorithm or function. And we do this by adjusting the 3 coefficients, one for the proportional, another for the integral, and the last one for the differential. And if we do that, we can actually obtain a more steady output without overshoot, as you can see on this one. So if we change the coefficients here, you can see that it has 3 different effects. So the last one where we've got 1.6, there's a fair bit of overshoot. Okay, so let's go and have a look at some of our software. Okay, so let's explore some of the software. And in this particular version, it comes from Pedersen, and I've made a couple of modifications. I'll show you my modifications first. So I've enabled remote control either by setting an A for ARM, a D for demo number, or an S for resetting. The resetting is the first time I've done a software reset, and if that flag is set, it will go back and reset the microbit on the drone. I'm also monitoring additional parameters: the ARM, the demo number, and the error, the derivative, and motor A and motor B. And we can see those when we look at the Makcode serial monitor. And just walking through the other bits of the software, right at the start, we're initializing all the variables and setting up the IMU and the motor control. And the buttons on the microbit, A and B, are used for setting the roll and pitch D and P parameters, and we arm the microbit by pressing A and B together. So that's the whole of the software. But you don't really see much on this view, except you can see where we're reading the gyro values. If I just in the forever, after we've got the right demo and the arm, and it has been armed, we calculate the angles. The throttle has been set to 31, and you can see we're going through the PID parameters. Then we set the motor speed for the 4 motors. But in this case, we're only using 2 motors, so motor A and C are being fired. Now, you really need to go to JavaScript to see in more detail what's going on. So if we go down and have a look at custom and go right down to the end of that, you can see the functions for the PID algorithm. So let's have a look. So around about here, here we are. We're calibrating the gyro here, and just a bit further on is the start of our PID algorithm. So you can see what we're doing here. We're doing the calculations for roll, pitch, and yaw. But in this case, we're only actually going to demonstrate the roll, and all the way down we're making that adjustment. Then right at the end, we're doing the motor control, and that's our software for the PID demonstration. Here I'm going to reset the Airbit2 controller remotely. So on the remote I'm going to press C, and we go through the routine to initialize our Airbit2. So we're displaying the program. We're on group 6, radio group. It's found everything. It's now calibrating. So it's now calibrated. And what we'll do is we'll start up with and we'll set it into demo number 1. And to do that, we just press the button here.